Today we're going to learn about a new rule that you're going to wish you knew a long time ago. Okay, this is going to make finding certain kinds of limits a little bit easier for you. Okay, and you're going to wish, oh man, this would have made the Unit 1 test far easier. Yeah, if you knew this rule. Yeah, if you knew this little trick. So anyway, this is a rule not for finding derivatives, which I know we've got like a whole list of derivative rules that you're supposed to know, but this is actually a rule to help you find a limit. Okay, this was developed by good old Johann Bernoulli. Okay, but Guillaume, which is like French for William. Okay, de l'Hôpital gets all the credit. Okay, I think maybe he published it or whatever, but yeah, it really came from Bernoulli. It's really his rule, but he doesn't get any of the credit. That's okay. He gets a shout out on the notes today. That's about as far as we're going to talk about him. So yeah, let's review how we find some certain kinds of limits here. So let's take a look at these. All right, just gonna blast from the past here. Back to Unit 1. Let's see what you remember. This stuff is still going to be on the AP test, so hopefully it hasn't escaped you too badly. So number 1 says the limit as x approaches -1, and then equal of this fraction, and we want to know what does that limit equal. So just as a little refresher, a limit is asking you to find what the value of the function is approaching, not necessarily what it equals. Although it could be what it equals, it all depends on whether or not the limit exists there or not. So you try, at least at first for all of these, to just simply substitute in the -1 or whatever the x is approaching and try to get a value out of that. And if that works, great, then you're pretty much done. But if it doesn't, then we have to think about it a little differently. So with this one, obviously, if we try to plug in -1, it doesn't work, right? We get a divide by 0 error. So we approach it a little bit differently, and we factor out a 2 in the numerator. So we have the limit as x approaches -1 of 2 times x minus 1, x squared minus 1 over x plus 1. And that x squared minus 1 is the difference of two squares, so we can factor that a little further. All right, so that'll be the limit as x approaches -1 of 2 times x plus 1 times x minus 1 over x plus 1. Now, normally you wouldn't be able to just cancel out those x plus 1s because you would be changing the function. But what you're actually changing by doing that is you are filling in the hole that common factor is causing. So the fact that we've got an x plus 1 in the numerator and the denominator here means that you've got a hole in the graph at x equals -1. And if we cancel those out, what that effectively does is fill the hole. So it basically includes that x equals -1 in the domain. Everything else is going to have the same output. So normally you can't do that because those two functions aren't actually equivalent. But in the context of limits, you are allowed to do that because it doesn't change the value of the limit. The value of the limit does not depend on the function being defined there. It just depends on whether or not the left and the right-hand limits equal each other, which they would in the case of a removable discontinuity or a hole. So, long story short, we are just going to go ahead and cancel these x plus 1s out. We're only allowed to do that within the context of limits. And so we get 2 times x minus 1. And at this point, we won't have any problem using a direct substitution. We just simply plug in the -1, and we'll get our answer. So 2 times -1 minus 1 would be 2 times -2, which would be -4. So we're just going to plug in that -1 right here and get our answer. You guys remember doing this like back in, August, September-ish? Starting to come back to you? Okay. The best time to review something is right before you forget it. Yeah. Number 2. Okay, now we've got an infinite limit. Okay, or a limit as x goes to infinity. How do we handle this? Obviously, we can't plug in infinity. That's not going to work. Yeah, you look at the powers. Yeah, so when x goes to infinity, what we're really interested in is what's the horizontal asymptote, right? What value is the function approaching? That's determined, or not determined, but that's defined by the horizontal asymptote. So the way we find the horizontal asymptote on these rational functions is we look at the degree of both the numerator and the denominator. And you ask yourself, like, what is growing faster? Is the numerator growing faster or the denominator? If the denominator is growing faster, like you have an x cubed on the bottom and an x squared on top, then the function is going to go to 0. If it's bigger on top, then it's going to diverge to either positive or negative infinity. And if they're the same, like in this case, how do you determine that limit or that horizontal asymptote? Yeah, just divide those leading coefficients. So you look at really the biggest two terms, right? And we could say that this limit equals the limit as x approaches infinity of 3x squared over 2x squared. And just like in the last one, normally we couldn't cancel out the x's because x can't be 0. But in the context of limits, we are allowed to do that. So this is just going to simplify and be 3/2. Okay, so just to kind of go back real quick, with number 1, if I tried direct substitution and plug in this -1, and I plug it into both the top and the bottom, what I get is a situation where I have 0 over 0. This is the case where you have a hole. Okay. Now, if I try to plug in infinity, which obviously I can't, but if I try to take x as x goes to infinity, if I just plug in some just obscenely large number into x here, we can see that both the numerator and the denominator are going to infinity. Okay, so the reason why I'm writing like infinity over infinity and 0 over 0 here is just so you can start to see how these limits get classified and start to associate them with the techniques we use to solve them. All right, any questions so far? Number 3. Okay, here we're trying to send x to 7, but if we try to plug in 7, that's going to make the denominator 0. Right? And if I plug in 7 in the numerator, 7 plus 2 is 9, square root of 9 is 3, 3 minus 3 is 0. So we get the 0 over 0 situation again. All right, so we have a hole that we need to fill. We want to find a factor that we can cancel out. And so to get that factor, when you have this square root situation set up, is you want to multiply both the numerator and the denominator by the conjugate of the expression that has that square root. So we're going to multiply both the top and the bottom here by the square root of x plus 2 plus 3. All right, we'll multiply both the top and the bottom by that. And then we'll simplify a little bit, not too much, but this will equal the limit as x approaches 7 of, in the numerator, if we multiply, we're going to like FOIL this out, right? First outside, inside last. We're going to multiply first the roots, but root x plus 2 times itself is just going to be x plus 2. And then the outside and the inside terms will cancel out because 3 times root x plus 2, negative 3 times root x plus 2 are opposites. And when you add opposites, it equals 0. And then finally, for the last term, we have 3 times negative 3, which is negative 9. On the denominator side, we're just not going to simplify anything here. X minus 7 times root x plus 2 plus 3. But now let's take a closer look at that numerator. Plus 2 minus 9 is minus 7. So we have x minus 7 both on the numerator and the denominator. Those can cancel out now, leaving us with the limit as x approaches 7 of 1 over square root of x plus 2 plus 3. And as soon as we cancel out that common factor, or that close up that hole, now we can use direct substitution. We can plug in that 7. Yeah, 7 plus 2 is 9. Square root of 9 is 3. So we get 1 over 3 plus 3, which is 1 over 6. Any questions about number 3? All right, let's take a look at number 4. What can we do here? How do you know it's 0? Yeah. If we look at those first terms, notice how this is a bigger on bottom scenario, right? So it's just going to be 0. And the denominator will grow faster than the numerator. If I, tried to plug in infinity, I would get this like infinity over infinity. Yeah, that doesn't really work for us. It's kind of weird. Okay, we get just a couple more throwback examples here. Number 5, you could try to plug in 6, but you're going to get 0. 0 over 0 again. So this is a case where we want to try to look for something to cancel. Now, if you factor out that numerator, you're going to get x minus 6 times x plus 4. But that doesn't exactly cancel out with 6 minus x. Exactly. Okay, good. I'm so glad you remember. So if you get that case where they're like almost the same, but the signs are just opposites, then you can factor out a negative 1 out of, in this case, I'd probably take it out of the denominator. And then I would have that common factor. Once those x minus 6's get canceled out or reduced to 1, you can go ahead and just use direct substitution here. And plug in that 6. So I get 6 plus 4 is 10. Divided by negative 1 is negative 10. Okay, last one. What's going on with number 6? How do you know it's negative infinity versus positive infinity?
Because there's a negative at the infinities can be multiplied by 3.
Yeah, we just want to look at these first terms on these x to infinity limits. And you can actually get 3 of those x's to cancel out or reduce. So this would be the limit as x approaches infinity of, negative 3x squared. And now if you think about just raising this x to be as big as infinity, right? Just keep making that bigger, times negative 3. So you have like 100 million bazillion times negative 3. That's going to be a negative number. So this is going to veer off to negative infinity. Yeah.
When is it?
Say that again?
When is it does not exist?
So in this case, the limit would not exist, like from a technical standpoint, okay? Because the limit's got to approach a number to be able to exist. So what we're saying with the plus or minus infinity here, like if you get positive or negative infinity, is that the limit doesn't exist because the value of the function's approaching either infinity or negative. Now, there are some other reasons why a limit might not exist. If the left and right-hand limits don't equal each other, then it doesn't exist. If you've got oscillating behavior, it doesn't exist, like sine x. As x goes to infinity, it doesn't like settle on any number, just oscillates between two values. In that case, it wouldn't exist also. Yeah. Okay, good questions, good questions. Okay, so this is all old stuff. You guys already know how to do this, or you've forgotten and you just relearned it. Yeah? One of the two, probably. But there's actually a slightly easier way of handling a lot of these problems. Okay? And that is with L'Hopital's rule. Okay, this is a good one. I think you're going to like this one. Okay, I couldn't teach you this back when we had limits because we didn't know what a derivative was. But now that you know what derivatives are, we can say that if the limit as x approaches some number of f of x over g of x is indeterminate, Okay, and by indeterminate, what I mean is if you use direct substitution, you get something like 0 over 0 or infinity over infinity, something like that, where it's sort of an undefined value. Then the limit as x approaches a of that fraction is equal to the limit as x approaches a of the derivative of the numerator divided by the derivative of the denominator. So now that you know this rule, you'll never have to ask yourself, oh, is it bigger on top? Ever again. Is it bigger on bottom? You'll never have to answer that anymore. Because now what you can do is just differentiate the numerator and the denominator like separately from each other, and then use direct substitution. Okay, so let me show you an example here. So these are the same problems we did on the front, but instead of doing it the old-fashioned way, we're going to use L'Hopital's rule. All right, so like number one, same problem as before, but in this case, if we try to plug in -1, we get 0 over 0, right? That's what we call an indeterminate form, where you can't just use direct substitution. But what we can do is use L'Hopital's rule and say, okay, well, this is going to equal the limit as x approaches -1 of the derivative of the numerator divided by the derivative of the denominator. So what's the derivative of the numerator? 4x. What's the derivative of the denominator? 1. So now we can just plug in -1 and get -4. How about that?
That's a little easier.
That's pretty nice, yeah? That's pretty good. This is going to change the game for you. As far as limits are concerned, it's a real shame we didn't know what a derivative was when we did limits initially. All right, number 2. Let's try it again. Okay, number 2, if we try to plug in this infinity, like obviously we can't plug in infinity, but if we could, we'd just end up with infinity over infinity. This is another indeterminate form. So let's try to use L'Hopital's rule. This is going to equal the limit. As we already know what the answer is going to be, by the way. We know it's going to be 3/2. Yeah. 6x over 4x, right? Which will equal the limit as x approaches infinity of 6 over 4, which just equals 3/2. Now, if your numerator and denominator are polynomials, it's pretty easy. And if it's not, you might have to use one of those other derivative rules. Right? Like number 3, you know how to solve this like with conjugates. Kind of annoying, but you can do it. You don't need the conjugates. You can just use derivatives. Use L'Hopital's rule here. Okay, if I try to plug in 7, I'm going to get 0 over 0. That's an indeterminate form. So let's use L'Hopital's rule. We're going to think of this x plus 2, or the square root of x plus 2. Think of this as like x plus 2 to the 1/2 power. Okay? And so we're going to have to use power and chain rule on that numerator. So this is going to equal the limit as x approaches 7 of 1/2 times x plus 2 to the -1/2 times the derivative of the inside there. So what's the derivative of x plus 2? 1. Okay, so I'm just going to do a times 1, even though I really don't need that. And then the derivative of 3, or -3, which is 0, so plus 0. We don't really need that either. Divided by the derivative of the denominator, which is just 1. So yeah, a whole lot of nothing that we don't really need in that expression, right? We don't need the times 1, the plus 0, the divide by 1. None of that is really going to change anything. So really, we just have this expression in here. And we're not going to have any divide by 0 errors. Yeah, you could just plug in 7. So this is going to equal 1/2 times 7 plus 2 is 9 to the negative 1/2 power. So what is, let's review here. This might be the place that trips you up. What is 9 to the negative 1/2 power? Yeah, 1/3. Okay, great. Okay, fantastic. So we got 1/2 times 1/3, which is 1/6. Now, I do want to remind you that this is a really nice rule and a nice trick, but it doesn't work for all limits. It only works for limits that have an indeterminate form. Like, in other words, when you try direct substitution, you get like 0 over 0 or infinity over infinity or something like that. But that's okay. If it doesn't work, you can just use direct substitution. Don't forget, that is an option. Like for number 7, you can't, if I try to use L'Hopital's rule here, okay, so this is going to be wrong, but if I tried to use it, I'm going to get that this equals the limit as x approaches 8 of 2 over 1, which would be 2, right? But that's not actually the right answer. That's the wrong answer. The right answer is going to be what we get when we substitute 8 in. So if I just do direct substitution here and get 2 times 8 plus 5 over 8 minus 4, I get 16 plus 5 is 21, and 8 minus 4 is 4.
So it only doesn't work when you can direct substitute, right?
Well, let's say a different way, that it only works if the limit has an indeterminate form.
Okay.
Okay, so yeah, this doesn't work. So even back when we were learning limits initially, your first option is always going to be to plug in the number. Yeah? And that's still true, because if that works, then you don't have to worry about any of the other techniques, including L'Hopital's rule. But if it doesn't work because you get an indeterminate form, that's where you want to fall back on this rule. Any questions so far? Okay, good. Yeah. I had a feeling you guys are going to like this one. All right, so we'll just do a little bit of practice here. Now, as we go through these practice problems, you always want to start with direct substitution if you can. And if it doesn't work, decide, okay, wait, is this an indeterminate form or not? What's happening here? All right, so number 8 says the limit as x approaches 3 of 2x minus 6 over x squared minus 9. If I just try to plug in 3 there, I'm going to get 0 over 0. This is an indeterminate form, so this is an example of one we can use L'Hopital's rule on. So this will equal the limit as x approaches 3 of 2 over 2x. And now I can just use direct substitution. So 2 over 2 times 3 would be 6, and so I get 1/3. Notice no factoring required. Yeah. No factoring, no multiplying by conjugates, no finding common denominators and all that stuff. It's great. Okay, number 9. If I try to plug in infinity, sort of in quotes there, it's not going to work, right? I'm going to get this whole infinity over infinity business, whatever that is. So we can use L'Hopital's rule. Yeah. Now, if you remember how the horizontal asymptotes work, and you can just see that this is going to be 5/3, and you just want to jump straight to the answer, you're still welcome to do that. All right? Don't feel like you have to use L'Hopital's rule. But if we did, it should still give us the 5/3. Okay, so the limit as x approaches infinity of 2 times 5 would be 10x minus 3 over 6x. Yeah, and we're still kind of stuck in the same spot, right? This is going to equal the limit as x approaches infinity of 10x over 6x, which would be 10 over 6, which is 5/3. But on a problem like this, it's still helpful to know what's going on with the horizontal asymptote, because we could have just got that straight from the beginning. Yeah. So find the ratio of those leading coefficients. Number 10. If If I try to plug in 0, I'm going to get 0 over 0. Right? E to the 0 is 1. 1 minus 1 is 0. So we're going to use L'Hopital's rule here. So this is going to be the limit as x approaches 0 of the derivative of e to the x is just e to the x. And the derivative of negative x is negative 1. Derivative of negative 1 is 0, so I'm not going to write that. Over 2x. Now it's still 0 over 0. It's still indeterminate. So we're just going to use L'Hopital again. And you just keep using it until you get one that works. Yeah. So this is going to be the limit as x approaches 0 of e to the x over 2. And now all of a sudden it works. I could just substitute in 0, and I get 1 over 2. So you might have to find the second, third, fourth, fifth derivative, however many times it takes, to simplify, or not really simplify, but use that L'Hopital's rule over and over until you get it into a form that is no longer indeterminate, where you can just use the direct substitution and get your answer. Usually it won't be more than like 2 or 3 times max, hopefully. All right, number 11. This is one that I really couldn't have asked you in Unit 1 because we don't know how to answer this question yet. Okay, if I try to plug in 0, sine of 0 is just 0. So this would be a 0 over 0 case. And yeah, you would probably be pretty lost if this was back in Unit 1 because we didn't have any techniques to deal with this. Not only that, but we didn't know like the derivative of sine or what a derivative even was, much less know anything about chain rule or anything like that. But we're going to use L'Hopital's rule here. And so we're going to differentiate both the numerator and the denominator. The derivative of sine is cosine, but we do have to use chain rule here because it's not just sine x, it's sine of something. So whenever it's like more than just x, you've got to multiply by the derivative of that inside. So this is going to be cosine of 2x times 2 over cosine of 3x times 3. Now I can plug in 0 because what's cosine of 0? 1. Right, if I just plug in 0, cosine of 0 is 1. So I'm going to have 1 times 2 over 1 times 3, which is 2/3. For number 12, can't really plug in infinity. I'm going to get infinity over infinity. So I'm going to have to use L'Hopital's rule here. Now, let's say you don't know anything about L'Hopital's rule. Let's say this is a problem, back in Unit 1, I could have given you this one. Because one of the things we talked about was the relative growth rates of different types of functions, right? And what grows faster, a polynomial or an exponential? Exponential always grows faster, right? No matter what the base or the power is. Now, if you have 2 different exponentials, we can talk about which grows faster. But if it's just an exponential versus a polynomial, exponential will always grow faster no matter what the base or the degrees are. So in the long term anyway. So since the bottom is going to grow faster, what do we know the limit's going to be here? Yeah, it has to be 0, right? So we know this is going to be 0. And even if you didn't know that, you could play around with L'Hopital's rule here and get the limit as x approaches infinity of 2x over e to the 5x times 5. Now, we're still not at a point where we're going to get something other than indeterminate. If I plug in of infinity, 2x is still infinity. So I'm going to have to run it again. All right, so I'll get 2 over, well, the derivative of e to the 5x is still e to the 5x times 5. And then I have an extra times 5. So I've got e to the 5x times 5 times an extra 5.
Why doesn't x times 5 get cut from the?
We're not adding 5, we're multiplying by 5. So it's like if you had a derivative like 4x, it'd be 4, right? That coefficient's going to stick with there.
Yeah.
And so hopefully now you can see a little more clearly, if the denominator is going to infinity and the numerator is just 2, it's not changing, right? The denominator is getting bigger and bigger. This whole thing is going to be getting closer to 0. Yes, ma'am?
Why don't you have e to the power x plus 2 if you do
Yeah, so let's break down that
Why
derivative.
don't you do you're taking the derivative of it, why don't you do the product rule?
Product rule. What's the derivative of 5?
1, 0.
0, right? So that other term is just going to zero out anyway. Normally when you have a coefficient, like let's say we have like 4 times x squared. Normally you would not use a product rule here. You just say it's like 8x, right? That coefficient is just going to drop down. Now you could use product rule, like technically you could, but what's going to happen is you have the derivative of 4, which is 0. So you have 0x squared plus 4 times 2x, right? So that same sort of thing is going to happen up here with if we have 5 times e to the 5x. If I want to use product rule there, then the derivative of 5 is going to be 0, and so I'll have 0 times e to the 5x plus 5 times e to the 5x times 5. So that term that you're looking for is going to zero out. And so you don't need to worry about product rule if one of the factors is a constant. That coefficient is just going to fall down because of what happens here. Does that make sense? Yeah. Good question. Yeah, that's a really good question. That's the nice thing about some of these rules is they still work even in scenarios where you wouldn't use them. Yeah. Okay, number 13. This is our last one. No, we got 2 more. Okay, 13. We got the limit as x goes to infinity. And we've got the natural log of 2x plus 5 over x plus 8. Now, this is another one where if you know the relative growth rates, you can answer this pretty quickly. Okay, what grows faster, polynomial or logarithmic? Polynomial grows faster, right? So we already know, like off the bat, this is going to equal 0. Yeah. Even if trying to plug in infinity is going to give me infinity over infinity. If you know about the relative growth rates and like what happens when one thing's bigger than the other, then yeah, we know this is going to go to the 0. If we try to use L'Hopital's rule, we can even verify that. Okay, the derivative of the natural log of 2x plus 5 is going to be 1 over 2x plus 5 times 2, all over the derivative of the bottom, which is just 1. So we can clean that up a little bit. Say that this equals the limit as x approaches infinity of 2 over 2x plus 5. And now we could see a little bit easier like why it would be 0. Because if we plug in infinity, this denominator is obviously going to get really, really big, and the numerator is not changing. So it's like equivalent to having something like 1 over infinity. Right? If you divide a small number by an extremely large number, it's going to get closer and closer to 0. So this is going to equal 0. Again, you don't necessarily have to do it if you know your horizontal asymptote rules. Okay, last question. Use the graph below to evaluate this limit. And so we're going to use L'Hopital's rule here. Okay, if I try to plug in 1, okay, let's just try to plug in 1 here. So f of 1 squared minus 4 over g of 5 times 1 minus 2 times 1. Let's just see what happens there. So I'm going to say maybe it equals that. We don't know. So f of 1, if you look at that graph, is 2. Yeah. So we have 2 squared minus 4 over g of 5, so 1, 2, 3, 4, 5. Let's see. I think this line might have got off a little bit. 1, 2, 3, 4, 5. Yeah, I think that line got messed up. Oh, wait, no, I'm looking at the wrong function. I'm looking at f. Sorry. That actually works out pretty nice. There you go. It's 2. Okay, so yeah, we get 2 minus 2. I was kind of worried that wasn't going to work out. So yeah, we do get a 0 over 0 situation here, right? This is an indeterminate form. And so that we don't know our answer. But we could use L'Hopital's rule, hopefully, and get a better answer. So this is going to equal the limit as x approaches 1 of the derivative of the top. So 2 times f times f prime. Now using that chain rule. Minus 4 would be like minus 0. So you don't really need to write that, but I'm going to write it anyway. Over, we're going to use chain rule again here. G prime of 5x times 5 minus 2. And now we're going to try to plug in 1 here. And if we still get indeterminate, we'll just have to run the rule again. And hopefully eventually we can just plug in 1 and get our answer. Okay, so plugging in 1, we'll put a little question mark here. Maybe this equals, maybe not. 2 times f of 1 times the slope at 1 over g prime at 5 times 1 is 5 times 5 minus 2. Okay, so f of 1 we established was 2. So 2 times 2 times the slope at 1. What is the slope of f here? Yeah, it's 2. Up 2 over 1, up 2 over 1. Yeah, good. So the slope is also 2. Divided by the slope of g at 5. Okay, what's the slope of g at 5? So right here. Okay, 2/3. Yeah, up 2 over 3, up 2 over 3. Very good. So that's 2/3 times 5 minus 2. So, yeah, so this would be 2 times 2 is 4, times 2 is 8, over 2/5 times 5. That works out nicely. Oh, 2/3. Oh, that doesn't work as nicely. Yeah. 2/3 times 5. That's okay. We get 10/3. Actually, we'd have a problem if it was 10/3. 10. Yeah, because it'd be 0. Yeah, if it was 2/5. Yeah, then we have to do the rule again. But no, we're going to be okay here. So I'm just going to clean this up here. Yeah, 10 minus 4, 2 would be 6/3. So you have 8 divided by 4/3, which would be the same thing as 8 times 3/4. Really messing with our fractions here. 8 times 3 is 24, divided by 4 is 6. Yeah. Okay. And that's L'Hopital's rule. Okay? Any questions? Oh, go ahead and pass that.